JavaScript can behave weirdly sometimes. Knowing what mutability in JavaScript means can help you understand this behavior in JavaScript as well as other languages. Before we begin, take a moment to think about the following questions. What exactly happens inside the computer when you create and mutate or change variables? What is the difference between let and const in JavaScript? Why is it possible to alter the properties of an object or add elements to an array even after declaring it with const? The answers to these questions all lie in understanding mutability and immutability. What is mutability? Mutability refers to whether a data type's value can be changed after it's been created. It defines the way the two main categories of data types, primitives and non-primitives, store data. To better understand this concept, let's take another moment to revisit what variables are in JavaScript. In JavaScript, variables are declared using two keywords, let and const. Before we delve into the difference, let's see what their similarities are. They act as pointers to an address in the computer memory where a value is stored. The keyword there is pointers because the variables do not store those values themselves, but point to the address where those values are actually stored. Consider this expression, let x equal 10. Normally, you would think that we just put the value 10 inside the box labeled x, but that's not exactly it. Let's visualize this differently. Imagine the computer memory as a grid where each cell represents an address where a value can be stored. And we had our variable x directly pointing to the value 10 stored in the computer memory. Now that we have a clearer picture of how variables store values, let's move on to mutability of primitive data types. Primitive data types are immutable. But what does that mean? It means that their values cannot be altered or changed after creation. When you perform an operation on a primitive, you are not changing the original value. You're simply creating a new one instead. Common examples of primitives in JavaScript are string, number, boolean, null, undefined. Consider this code snippet. Let x equal 10, x equal 5, console.log x. What will the value of x be? 5. Wait a minute. Didn't we just change the value of x from 10 to 5, even though we just said primitives are unchangeable? Well, no, we didn't change the value 10 to 5, even though it appears so. So what did we actually do? We moved the x pointer from the memory address containing the value 10 to one containing the value 5. Let's head back to our previous analogy to visualize and explain what happened. We have our computer memory over here and the variable x over here. After the first line of code runs, x points to the value 10. On the second line, where we reassign x to the value 5, we move the pointer to another address containing the value 5. Okay, so we didn't change or replace the value 10. What then happens to it now that no other variable is pointing to it? The JavaScript engine has a feature called the garbage collector that periodically scans the computer memory for values without a pointer and removes them to create space for other values later on. The key takeaway is that when we reassign a primitive declared with let, we are moving the pointer, not changing the value. But what if we declared it with const instead? Still the same example, but declared with const. What is the value of x? We get an error. But why? Back to our analogy again. On the first line of code, we have the variable x pointing to the value 10. Notice that aside from the color being different, this pointer isn't dotted like the previous let pointer. On the second line of code, we try to move the pointer to another address containing the value 5 and run into an error. Here's why. We get an error because declaring a variable with const means binding the pointer to the address it initially pointed to, and trying to break that bond by moving that pointer would cause the JavaScript engine to throw an error. Let's consider this example with string. What will the value of message be? Lowercase hello. But why? The message variable remained lowercase because of the immutability of strings. The toUpperCase method does not change the value of message. Instead, it returns another string that we can reassign back to the message variable. From our previous code snippet, if we wanted to get the desired result of uppercasing the word hello, we will need to reassign the message variable like this. Once again, let's revisit our analogy to visualize the process. We have the computer memory and the message variable pointing to the string hello. On the second line, where we ran the message.toUpperCase, a new uppercase hello string was created and stored in the computer memory, but notice no variable points to it yet. Finally, when we reassign message to the return value of the toUpperCase method, we move the pointer to the new location. Still remember what happens to the previous value? That's right, it gets garbage collected to create room for other values. As we saw just now, the initial lowercase hello string was not changed, but a new one was created, and the pointer was moved to the new address storing the uppercase value. This process is the same for all primitive data types. Let's shift our focus now to mutability of object data types. Object types are mutable. What does that mean? It means their properties or elements can be changed. Some common examples of objects are objects, arrays, functions, date, set. Consider this code snippet. What will the value of bio.age be? As expected, 30. Now, let's visualize how objects are stored and accessed in the computer memory. Unlike primitives where the computer allocates a fixed size for storing them, the allocated size of object types are typically larger. When we assign a variable to an object, the pointer does not actually point to the object itself, but to the hexadecimal address where the object is stored. When we access the age property using the dot notation or the bracket notation, that's when we are looking into the content of the address. Now consider this mutation example. What will the value of bio.age be? As expected, 50. Although this looks quite similar to how we reassign primitives, but internally it works differently. Let's see how that works. As explained earlier, the bio variable points to the hex address and not the object itself. On line 2, where we change the age property to 50, the object becomes. The key point here is the bio variable maintained its reference to the memory address, but we can access and change the values the object holds using the dot or bracket notation. It is also worth noting that declaring the object variable using const would work the same way as using let, because we did not move the pointer. Because of this, it is advised to use const, especially when dealing with object types, because when you use let, it is still possible to reassign that object back to another data type, which can lead to unintended bugs. Let's consider this final example with arrays. What will the value of colors be? Red, yellow, blue, and green. Now, back to our grid. Similarly to object literals, variables assigned to arrays store the hex address, not the array itself. The push method adds an element at the end of the array. The pointer remained intact, but the content of the array was changed. To summarize, Primitives like strings, numbers, booleans are immutable. Their values cannot be changed after assignment. Object types like objects, arrays, functions are mutable. Their values can be changed regardless of whether they were declared using let or const. Variables are pointers that reference a value or address in memory depending on the data type. Declaring a variable with let means you can move that pointer, while declaring the variable with const means the pointer is immovable. Thank you for watching. If you found this helpful, please like, repost, and share with your friends. You can also follow me on X at Rolex__dev and on YouTube at Rolex_dev with a triple V. Until next time, bye bye.